Okay, so in the last video, we got started on some string helper stuff for the code base. One important thing that I end up wanting is the ability to convert strings of different Unicode types. This is especially important when building on the Windows operating system, since their APIs all use UTF, but on Linux, it's going to use UTF-8, and for common file types that you're going to use, it's going to be UTF-8 most of the time. So it's useful to be able to convert between those so that you can make a single interface for them that uses the same string format, and then the Windows one can just automate the conversion in and out. The other nice thing about having these is if you do a 32-bit version or the UTF-32, that UTF-32 is basically the same thing as just turning a Unicode stream of whatever encoding into just an array of code points that you can easily deal with. It's easier to do things on UTF-32 since everything is the same size. It's just an array of 32-bit integers at that point. So sometimes when you're doing something like font rendering, text rendering stuff, it can be handy to be able to get to a 32-bit code point too. So we're going to take a little time today and just write that stuff. The idea here is to write a converter that takes correct strings to correct strings and doesn't crash or do anything terrible on incorrect strings. That will be good enough for the requirements I have for this one. So this isn't like the beginning of a whole never-ending Unicode rabbit hole. It's just going to be some encoding conversions, and then we're going to move on. So for UTF-8, the idea is that it's encoded at a granularity of 8 bits, right? There can be multiple bytes together to encode one code point. So some of the bytes will by themselves correspond to a code point. Sometimes it'll be 2 bytes in a4 bytes in a row, or 4 bytes in a row that correspond to a code point. The way we can tell which of those situations we're in is by looking at the high bits of those bytes in the case of UTF-8, right? So a byte that begins with 0 is always a 1 byte encoding for a code point, and the other 7 bits are the value of the code point. In this one, what we'll see is that when we see a 110 in the first 3 bits of a byte, that lets us know we're seeing a 2-byte pattern. And then after that, we should see a 10 byte and a few more, of the bits coming on this one after the bits on this one. Hopefully that makes sense. So in this case, for instance, there's 5 bits here and 6 bits here, and when we put those bits together, we get 11 bits of the actual integer that's encoded by this. And every time we go down the row of this table, we see we get a little bit more in terms of the number of bytes that are used, and more bits that can be used to encode that are encoding the integer we care about. So the third line here, we have 3 ones and then a 0 on the high bits of the first byte, and that lets us know, okay, we're looking at a 3-byte sequence. Then we grab 4 bits here and 6 bits on each of the next 2 to give us 16 bits for that code point. Then the final one is, again, same pattern, right? 4 bits in a row now, and then a 0 and on the high bits lets us know that there's a 4-byte pattern. That only leaves us 3 bits on the first byte, but then we get, 18 more bits. So 21 bits in total on the longest possible encoding. So let's try to convert some of that, what we just looked at, into knowledge in our code now. Okay, so I just did my first pass just off the top of my head from the definition of UTF-8 as I understood it from looking at Wikipedia. So I made this thing called string decode. It's just a helper type. And the reason I made it is because when I do a decode off of one of these streams, I'm going to want to know at each point that I decode these two pieces of information. What is the code point you found at that location, and how big was the amount of data you ended up consuming? So that way, if I get that much information, then if I have a stream of these things, I can just apply a loop over them, incrementing by the size at each point and emitting code points as I go, right? That's the idea. It's the thing I need back from a decode operation on these particular encodings. So the other thing I ended up doing is this little trick where I was looking at the bit patterns here, and I thought, all right, first of all, there's only 5 bits in the number of, looking at the bits that matter for determining the length of the encoding, what sort of byte we're seeing, right? There's only 5 bits that matter. Even at its longest, right, 1110, this is the longest possible thing that actually means we have a good byte. If we see all ones on that part, we actually are in a that's an error. That's not a validly encoded UTF-8 stream at that point. But if we see this, then we know we have 4, and anything less than that, it's something less, 3, 2, 1, or 0. And that's only 32 bits. That's only 5 bits, which is 32 possibilities, which we can fit into a table, which is what I did. In fact, I could fit this into a smaller table, and it's probably what I should have done. Yeah. So I can fit this into a really small table of just 32 bytes, and now when I have a byte and I want out of the stream, right, I take a byte out of the stream and I want to interpret it, understand what role it plays in the stream, it's pretty easy. I just ignore the below 3 bits by shifting them out and look it up into this table to find out what class of UTF-8 byte I just got. Then I process it according to the rule for that byte. So if I get a 0, that means it's just the low 7 bits form the code point. In fact, since I know that it's 0, I could actually do this. If it's 2, 3, or 4, then I know I have an encoding of that length, so I need that much space to be in the cap for it to work. And then I need, and the cap is like the size, right, of what's the capacity of the buffer I got passed, so that I know how much I'm allowed to parse. So if I grab the extra bytes that I need, make sure that they're all class 1, and so if everything's valid, I then set it up. Oops, I didn't finish this. This should be a 3 and a 4. Obviously, I haven't tested it yet, or I would have seen that. But anyway, it should be able to decode them. Now, like I said, it's not tested, and I'm not 100% happy with it. I feel like this is definitely the kind of thing that is at the limit where if I thought about it some more and I tinkered with it, I might come up with something better, and other people might have come up with something better too. So this is kind of where I look at it and think, okay, I have an interesting problem on my hands now. I have pieces that I can compose and a problem that I want to solve with them. I kind of like to think of it as like putting my mind into like Factorio mode or TIS 100 mode, or any game that involves constructing systems and optimizing them. It is time to put my brain into that mode. I have the problem definition is clear, what the inputs and outputs are. The pieces I have are clear. The systems in this language, the possibilities that the possibilities of what the processor can do. I need to just do some research, look around, see what I can find, tinker with it myself for a little bit. So I'm going to take some time to do that, and if I come up with something better, then I'll show you that. And if I think that this is as good as it's going to get, then I'll explain why. Okay, I found something that I like. I'm not going to copy paste this, but I do want to kind of give you an idea of what I've learned from it by going through it real quickly with you, and then we're going to try to do something similar in our version that we're writing right now. So I found this blog post on a branchless UTF-8 decoder that linked to a single header file that just includes this function. You can see it already looks kind of similar to us, but it's already a little different on this table, and it's got some extra tables that I didn't think of doing on a first pass. And I think looking at it here, it looks like less code too, which I'm especially excited about. I like the idea that it will work with less cases on a switch. So and the fact that it's branchless is also exciting. So we're going to try to learn from the patterns being used here and put them in use in our version. So this right here, you can see it's the same table I have, except I called them classes, and it's literally going with length. So it's putting ones in on the first ones, zeros in on the ones where I put ones, and instead of making a 5, it just goes back to 0 for the error spot there. So let's try that rewrite first. So that means these are all ones. There. Okay, so that's a little nicer. We got rid of a case at least, but we haven't changed much else. But we can keep going. So the other thing is, now the way it's set up, those are actually literally the lengths. The only thing is that when something's a 0, we're going to treat it like a 1 because we want to keep advancing even though there was an error. We want to just treat that byte as an error and move to the next byte. You know what I mean? So zeros makes it a little tricky, but we could make a parallel table. They're not doing this, but we could make a parallel table called advance, and then use the advance amount for determining what's next and use the length for other things. It's kind of interesting. Well, let's look at what else they're doing, and then we'll be able to just write it all in one go. So they've got masks. So these are the masks I wrote out by hand. The ones for if you have a 2-byte sequence, you want to drop the top 2 bits, then the top 3 bits, then drop the top 4 bits, then finally drop the top 5 bits. So though that's a good idea, let's just put the masks in there. That's the mask for that's the first bytes mask. What are these mins for? Okay, so this is for detecting errors that I'm not bothering with. So there's a non-canonical ways of encoding a character in UTF-8, since you could, for instance, use the bytes that make a 4-byte encoding, but then only use 7 bits so that it could have fit into 1 byte. And I'm not too worried about that. If I do want to detect that stuff, it'll be because I'm writing a more serious UTF-8 thing. But I want to get this just to the point where correct strings go to correct strings, remember? So we're not going to worry about error strings right now. Shift-C, 18, 12, 6. Okay, so that is the shifts for... well, let me see how it's getting used. What is that C thing there? So that's an output 32-bit thing. I see. So it's getting constructed on the top of the byte and then shifted into place rather than being constructed in place in the first initially. And I guess the reason for that is so that these can do the right thing, right? But how is this possible? So you're always ORing in the next bits here. Oh, but so if you read ahead, it won't matter if it goes and reads something that it doesn't need if we're just shifting it out at the end anyway. So then the only problem with this is we don't have any way of assuming that we actually have 4 bytes that we can even dereference. This is basically saying assume for the purposes of the branch list portion that we have some chunk we're going through, and we're always going to be able to read the next 4 bytes from any position. And if we were trying to make something that ran fast, that's probably what we would do, is we'd take the string we want to decode, we'd quickly copy it somewhere else, and set it up with a bunch of 0 padding at the end for those extra bytes and let it go. But we're not going to be able to do that. So I might not actually push it this far. Maybe it'll still be branchy in our version, but we can at least use this idea. I like this idea of constructing it down the top, and then maybe we make it a little loop instead. Okay, so I'm going to take a shot at doing that stuff. Okay, so that test convinces me that this decoder is pretty much working. So we can do one character at a time. I just want to wrap that up with a helper that does that puts an entire UTF-8 string in and a UTF-32 string out now. We'll also want to write a string encoder for UTF-8. Okay, so I think I'm happy with this way of doing the encoding and decoding. A quick test to sanity check, it looks like it's working. So yeah, that's how we'll do encode and decode on UTF-8. Now, what we'll do is we'll introduce a 32-bit version of our string type. It's not going to have all of the helpers that the string, the 8-bit string type has, but it'll just be used for the interfaces that do conversion in and out from UTF-8 to UTF-32 strings. We'll also need to write encoders and decoders for UTF-16 so that we can do directly from UTF-8 to UTF-16 conversions. But we'll do that after we've done the easier 32-bit conversions for this one. Okay, so it looks to me like our UTF-8 stuff is good to go. So we're going to do the same idea again, but now we're looking up UTF-16.